Done with this, and then this is what it would look like afterwards. Okay, I have put dots on them to make it clear for you guys. You don't put dots on it though. You just deal with the holes. Alright, so notice we have 4 vectors here. And we have 4 tables on each corner. So we gather the information for one vector and we fill it out with that table. And we gather information in another vector, fill it out of that table. And let's gather the information for this vector right here. Alright, so let's see here. We want to find the distance here between the first hole and the last hole. Okay, so it starts here, and I know it goes here, 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 but does it include this last hole here? In other words, is this last hole the first hole of the after the collision vector, or is it still the last hole of the before the collision? Well, I can double check that by just comparing the distances. I compare the distance between this and this one, and I compare the distance between that. Oh, no. Clearly, this is definitely the last hole in the before. So I find the distance now. I find the distance. Okay, so I get, let's see what I get. I have to be very careful here. I get 3.18. So for my 100 gram, I get 3.18 centimeters. All right, and now the time, remember I said that every dot represents 1/10 of a second. So I start with the first dot, 0.1, 0.2, 0.3, 0.4. Or we can just think of it this way. I have 5 holes, so it will be 0.4 seconds. If I had 6 holes, it would be 0.5. If I had 3 holes, it would be 0.2. So this is 0.4 seconds. And now I need the angle. To find the angle, I need a protractor, and I need a much longer line. I need to put a line, and I need to make sure that it's long enough, good and long, so I can use the protractor. If it's too short, I won't be able to use the protractor. So now I put the crosshairs right on the line. I make sure the horizontal crosshair is parallel with the horizontal lines on the paper. And then I'm ready. 135.1. 135.1 degrees. Okay, so now we want to fill out the rest of the table. Let's go to the board to finish this. All right, so this is where we left off. This is our vector, and this is what we found so far. The mass, the position, 2I, time 2I, theta 2I. Okay, now to find the velocity in the real world, we have to find the velocity in the paper world by taking S2I and dividing it by T2I, and then convert it to the real world with our scale factor. All right, so for this example, what do I have? What am I doing? So 3.18 divided by 0.4 seconds times the scale factor 13.8408. All right, so 3.1 incinerated divided by 0.4 seconds times the scale factor, and I get this number in centimeters per second. It's just for this example. All right, great. Now that I have the velocity, I can find the momentum by taking the mass, the 100 grams, multiplied by the velocity we just found, V2I. Okay, so what we now have is the polar representation of the vector. In other words, we have its magnitude now, and we have its angle. That's the polar representation. So now let's switch to a Cartesian representation. So I take this momentum now. To get the x-coordinate, I have to multiply by the cosine of that angle. So P2I times the cosine of theta 2I, that will equal that coordinate. And notice for this particular vector, it makes sense that we get a negative number because clearly that component is in the negative x direction. And we suspect a positive component for the y, and that's what we'll get. P2I times the sine of theta 2I. This gives us, for our example, this number. Okay, great. So we have finished gathering the information for one of the 4 vectors we need. Then we erase that pencil vector off your paper so we don't confuse it with the next 3, and we'll erase after each time. So let's just take a look at what the finished product will look like. Let's take a look at the finished product. I promise you, I'm sorry that I'm teasing you. I don't mean to tease you. I made you wait too long. I'm sorry. It hurts me more than it hurts you. That's what we have. And I've left the vectors here, even though you'll be erasing them after each time, just to make sure that you understand that they correspond to the 4 corners. Okay, great. So now notice, we have these sums in the middle. Okay, so what happens is you'll find these x components on the sides here, and you'll add them up for this one here. And then you add up the y components you just found for this one here. And then you'll have the x components down here for the initial, and then the y components down here for the initial. You add those up. So now let's just talk about some checking. Take the difference between the x values you just found here. In other words, this is now the x component of the total final momentum, and compare it to the x component of the total initial momentum. If these 2 values are greater than 600, you know you're screwed up. I say you should do it over. And then do the same, compare the y's. Compare the y values for the total final momentum and the total initial momentum. If they're greater than 1,100 momentum units apart, I say you're screwed up. I say you got to do those over. Terrific. Let's go to the board. Take a closer look at what we have. All right. So like I just said here, so this is the top middle part. And like I just said, we found the x and y coordinates of the total final momentum. That represented as a Cartesian vector is here. In other words, the x coordinate I hat plus the y coordinate j hat. We can switch to polar. In other words, take the square root of the sum of the squares of the x and y components. Great, to find the magnitude. And then the angle. The angle of the final total momentum is the arc tangent of the ratio of the y component over the x component. Okay, so now a little bit of warning here. You might get a negative angle. In other words, calculators tend to only give you angles in these 2 quadrants. So if you get a negative result, add 180 to it to get the angle you really want. All right, and then we do the same thing with the initial. This is the x coordinate of the total initial and the y coordinate of the total initial. Represented as a Cartesian vector, the x coordinate I hat, the y coordinate j hat, and then same thing. We switch to polar. We can switch to polar, taking the square root of the sum of the squares, and then use the arc tangent. Same thing again. If this is negative, add 180 to it.